So, good morning, ladies and gentlemen. Welcome to this NUS Robotics seminar today. I'm very proud to welcome you to this series, but I'm also very happy to introduce today's speaker, Professor Bruno Siciliano. You're in front of a big name of robotics, actually.
In terms of size.
Who contributed very much to robotics, especially control, manipulation. And he really contributed to the foundations of the field. And I'm sure that many of you maybe studied robotics and control in his book, Foundations of Robotics. But of course, he's also a great scientist doing a lot of research in this field. As I said, it's especially control, manipulation. You will see many difficult, many challenging manipulation tasks. So he's a prolific author. Papers, of course, but also books, as I mentioned. In science, he also got, he coordinated many projects, but he is especially the PI of prestigious projects that are granted by ERC, to the European Research Council. He is a fellow of many scientific societies. I will not mention them all, but I just want to mention the IEEE Robotics and Automation Society, where he's a fellow, but he really contributed a lot in the past. He's still an active member. He got to the the Pioneer Award from IEEE Robotics and Automation Society in 2004, and he served as the president of the society, 2008 and 9, right? Correct. Okay, so I'm not going to take more of his time. I didn't say the formal affiliation. He's a professor at the University of Naples, but he also has an affiliation with Buddha University. Yep. You can explain us better why and what you're doing there. So without taking more of his time, I just leave the floor to Bruno. Thanks a lot for coming and look forward.
Mi fai un paio di foto? Così le mando per LinkedIn. Perfetto. Sì, infatti. Okay, a very good morning to everybody. I almost got wet because we were just walking to visit the Advanced Robotics Center, and then I saw some setups, some research, and I saw the very famous research by Cecilia on the octopus robot. And being so wet, it just came up to my mind. There is a sort of way of saying into the dialect, into the Napolitan dialect, when you get, very wet, deep wet, we used to say, you are wet like porpetiello. Porpetiello is a small octopus. So there must be a conjecture between the fact that, I was visiting the research facilities on the octopus, and just by serendipity, by coincidence, we got wet because, octopus lives underwater. Okay, I just realized that my last visit here dates back to 2010, 16 years ago. It's amazing. I think I was a keynote speaker at ICAR CV conference. It's an international conference on advanced robotic computer vision. And I think I was invited by Marcello to give a talk. So 16 years. But, the good thing, the fun of being in research, that I'm 66 years old, but I don't feel my age because, you feel, I think it's a sort of antidote to getting old, because every new year I have a new class of students, and the amount of adrenaline when I go to class. Of course, they know me by name, by fame, and things like this, but it's always a new challenge, because you have to dive into the minds, into the souls, into the brains, into the hearts of the students. And this is giving me the same dose of adrenaline as probably you saw the background of my desktop, almost the same adrenaline when I go to the stadium to support Napoli football team. I'm a big football fan. It's a shame as an Italian to be here during the World Cup because Italy did not qualify for the third time in a row to the final round. And they even increased the number of teams from 32 to 48. And Italy was brave enough not to make it. Yes, it's kind of embarrassing. But you know, I love football. And when I started traveling around Europe to visit research labs, to go to conferences, each city I was going to the stadium because I like the atmosphere of the stadium, because the stadium from a sort of anthropological viewpoint is a kind of cut of the society, because you see like top people, like all the classes, like the social classes, the low classes, the middle classes, the high classes, and they all share this kind of passion for you know, just to be a football fan. In London, I've been 3 or 4 times to two games in the same day, because you know there are 6, 7 clubs in the Premier League in London. Yeah, but I'm not going to speak about football. We say football, but not to be confused with the American football. Maybe we should say soccer, because in the US they say soccer. I have just a few slides before my talk. My talk is about robot manipulation and control. I am a control guy. I'm a control professor. So typically, like control people, you know, just they apply their control techniques to different kinds of systems. And I studied, when I was doing my PhD back between 1983 and 1986, I was working I started from my mentor working on motor control for some kind of robust adaptive control, then to the task space with all the kinematics, redundancy, singularities, cooperation, manipulation, things like this. And I understood that robotics was not just applying a control algorithm to some kind of system, to drive a model and to apply, because the aspects, the issues of design, the issues of sensing, motion planning, are as important as the issue of control. And this is what now people are talking about physical AI, you know, which seems like a sort of hype. And just as a small parenthesis, I personally don't understand why the perception of the concept of physical AI that involves human-robot interaction and cooperation is confused with the acrobatic humanoids that do not interact with humans. We were talking with Cecilia. So physical AI and the humanoids, for me, are still 2 words apart, the way I perceive it as being robotics in 4 decades. But just have a few slides about my university. It's the oldest public-like university in Italy, and one of the oldest in the world. In Italy, Bologna is older, but Bologna and Padua, that was founded in 1222, 2 years before, belonged to the church. So it was not independent. So it just you had to belong to the circuit of the state of the church, you know, to be enrolled in university. And it was founded in 1224. And in speaking about engineering, in Napoli, we had the first school of engineering in Italy. It was founded by Gioacchino Murat in 1811. Gioacchino Murat was a general of Napoleon's army, and that time he was king of Naples, because we had 8 kings, because until the southern part of Italy was reunited to the rest of the country, we were the kingdom of 2 Sicilies. If we had stayed a kingdom, probably we would have been in the Champions League every year, and we would have won more titles because of the domination of the teams from the rich teams, from the wealthy teams from the north, like Inter, Milan, Juve, and things like this. Anyway, yeah, of course, you know, robotics and football are really interlaced. I don't know when one ends and the other starts, and the other way around. So we have 4 schools, 40 research centers, 26 departments, and a student population of 80,000 students. Napoli has a population of 1 million. So it means that you know, almost 1 out of 11, 1 out of 12 is a student in Napoli. So it's really a student town, because besides the main university, there are another 4 universities that are smaller than Università di Napoli, Federico II. And 2023 was a good year because we have a national program supported by the minister that is funding we call them departments of excellence. So it's the 180 top departments into the public university system in Italy. And in 23, it's renewed every 5 years. The university had 12 departments out of 26 awarded with Department of Excellence. So from the previous 5 years, we had only 5. And then, so we are the second in the country after State University of Milano, that's got 13. And we are first in engineering because 4 departments out of 5 are departments of excellence. And counting the heads, the faculty and the researchers, we are the #1 in the country for engineering. 3,000 faculty and research staff plus 6,000 administrative and technical staff, 85 doctoral programs, and also we have I know that according to the Anglo-Saxon system, the master follows the bachelor's. And this is what in Italian is laurea triennale, bachelor's, and laurea magistrale, the masters. But also we have some kind of postgraduate masters. There's like 1-year course, either after the bachelor, they're still called master because our master is called laurea. So it's like called master, but it's +1 specialization after the bachelor's or after the master. And also, we are quite active with the so-called academies. Academies are sort of professional courses offered in parallel to the university courses. So basically, for instance, in our department, we have the Apple Developer Academy. That is the only academy opened by Apple in Italy. And it's quite successful. So it's like students follow a 1.5-year course, and basically they just learn how to develop apps like software, and they get jobs in computer science. So this is our department. We have been Department of Excellence during for 2 consecutive terms. I'm a professor of control, and Cecilia, when she was at Scuola Sant'Anna, was a professor of bioengineering, okay? But robotics, as we know, it's very transversal. So it's that we don't have a scientific sector of robotics, because I'm in control, she is in bioengineering. Marcello is a mechanical engineer. So it's like, because there are several scientific sectors that contribute to information technology and electrical engineering. We have 18, so we are a very multidisciplinary department, and we are the largest engineering department. So these are the figures. I won't spend any more time. And just one slide devoted to my research team. PRISMA stands for Projects of Robotics for Industry, Services, Mechatronics, and Automation. We've been active since, I would say, 35 years. And so we are like 9 faculty, 3 full professors, 3 associate professors, and 3 assistant professors. And the other day, one of my former students, Fabrizio Caccavale, he was elected rector of the University of Basilicata. I realized that I'm growing. I don't want to say that I'm getting old, because 11 pupils that did PhD with me are already full professors in Italy and abroad. So it's quite a sign of age, I should say. And we got 25, even more. I think it's 28 European projects in the last 18 years, including 2 ERC grants. As Cecilia kindly mentioned, ERC grants are the most prestigious kind of grants. Typically, when you get an ERC grant, you are promoted to the next step of your academic career, because it's kind of rewarding. I was unlucky that I became full professor too early, that when I got the grants, I could not be promoted, I could not be upgraded, because we are kind of state employees, so I was already at the top. So patents, awards, and these are the research areas in which we're active. These are alphabetically ordered. It's like, although just industrial robotics was when I started working in robotics, then I would say like we work on human-robot interaction. A big portion of our research work has been on aerial robotics. And in aerial robotics, we have Neobotics. This is like a startup company by one of my former students, who is also a full professor. And he develops drones and hybrid robotic systems. I'm going to show some videos, some results from both from the research in the lab and also from his startup. And then we started working on medical robotics since 10 years now. And besides PRISMA Lab, we are active within the Interdepartmental Center for Advanced Robotics in Surgery. And this is a different lab that is located in the polyclinic where the surgeons are, because the physicians and the doctors and the surgeons, they don't have time to move in different parts of town. So strategically, our lab should be there, just where their needs arise, for research in surgical robotics. And then recently, we've been active in AI and cognitive robotics. Two of the faculty in our team are not engineers, they are computer scientists, because I really like to have a sort of interdisciplinary group. And also, following my ERC Advanced grant, we start working also on dynamic and legged robotics, although this is a sort of more recent work. This was kindly mentioned by Cecilia. This was a textbook, but it's now the old textbook, because this is the textbook that was published in 2009, and it was translated into Chinese, into Italian, because the original book was in English, and also in Greek. And this was a sort of accolade for me, because I did, in Italy, you do this high school, and you can do either the classical or the scientific high school. And since I was good in math and physics, I studied in the scientific high school. But I always like human sciences, like literature, like philosophy, like history, and also Greek. But I didn't study Greek. But at least I can say that I have a classic book in Greek, although this is the modern Greek, it's not the ancient Greek. And the other day, I got an email from the publisher, because we have a new textbook, Foundations of Robotics. This was published in September 2025, and the book is radically changed. It's been extended thanks to the contribution of a new co-author with us, because Professor Sciavico, who was my mentor, retired, is no longer active, and we were very lucky to recruit as a co-author Alessandro De Luca. He's a professor of control and robotics at Sapienza University of Rome. So this book is a book co-authored by two authors of Università Federico II, myself and Luigi Villani, and two co-authors from Sapienza University, Giuseppe Oriolo and Alessandro De Luca. Giuseppe Oriolo was the best PhD student that Alessandro had, like Luigi was for me. So it's a sort of, just as like, I don't want to, since I see many young souls in the audience, I just want to share like a few bites of my history, because when I did my PhD, I spent 1 year at Georgia Tech in Atlanta, in Georgia. And I went back, defended my thesis, and I had the opportunity, I was offered a tenure track assistant professor position at the Georgia Tech. And I was kind of attracted to accept. But this was '86. At that time, there was a man that changed the history of the city and our destiny in terms of football, soccer. Of course, I'm speaking about Diego Armando Maradona. And believe it or not, I refused the offer, and because I didn't want to miss. I had missed already the second year of Maradona because I was in the US, and I didn't want to miss. And so when I told to the youngsters, life is a sliding doors. You can go through or you can step back. At that time, I stepped back because I wanted to live the years of Maradona. I didn't want to be away. And I made the right choice because we were champions in '87. And 2 years later, Bernie Roth wanted to recruit me at Stanford University. He had recruited Usama Khatib earlier, and he wanted, I'm younger than Usama. I know Usama is a regular visitor here. And I was very tempted because I loved Bernie, I loved Usama. But I say, no, if you come, you have to stay 6 years. No. I was in the final triplet of candidates for the interview. And again, I say no. And I made the right choice because we were European champions. We won the championship. So, I mean, life is work, but life is hard, is passion. And there's a moment when you just consider sliding doors that you have to listen to your inner feelings and make the right choice. With some pride, I can say that the students at Georgia Tech, the Stanford, in major schools, they study robotics from our textbook. And for me, the name counts, But the real legacy that I have with my hometown, with my alma mater, is that they read Università di Napoli Federico II. That's the asset, that's the legacy. Because, you know, I would have become myself wherever I would have been, in Singapore, in Tokyo, in Sydney, or I don't know, in Boston. It just is like all places where I got offers, you know, just is like. But anyway, so this is a message that I want to share with the youngsters. I think it's good to follow your professional track, your wishes, your desire, but there's a moment in which you have to listen to your soul, to your heart. And this was the case of Foundations of Robotics. The textbook has been a sort of big challenge in my life, but the textbook, once you have a contract, you are the deadline. You are the one to deliver. Okay, so the commitment, it's a sort of challenge against yourself. But the challenge of the Handbook of Robotics has been incredible, because the success does not depend only on the two editors, the two co-editors, myself and Usama Khatib, because the success depends on the community. And this was a strong community effort involving 200 and more people. And this was, I had 3 kids. Well, for me, always kids. They are 30, 27-year-old, the 2 boys, and the girl, 24-year-old. She's graduating next month in biomedical engineering with a master, and she's saying that she wants to do PhD, I don't know. And, but the success depends on the community. And the handbook is my 4th child in all senses, because I devoted 12 years of my life, from 2002 to 2008 for the first edition, and from 2010 to 2016 for the second edition. And I just want to share. The second edition, when it came out in 2016, it's 10 years ago, was one of the first books where this concept of the multimedia embedded. You know, with an app, you can watch the videos, no matter whether you're reading the electronic version or the paper version. So it was quite a sort of innovation. And it got the Prose Award, which is this award that is given annually by the American Association of Publishers to the best books in each field. Springer had never won this award before our handbook. And 3 weeks ago, I was at the ICRA conference, International Conference of Bioautomation in Vienna, and we had sort of a handbook and star series lunch with the editor. And I came to know the current figures of the handbook, believe it or not, between the 2 editions, there have been 14 million downloads, paid downloads of chapters from the handbook. It's the second most downloaded book in the history of Springer. Amazing. And it's a pity that we didn't negotiate any royalty for the download with the publisher, because even €1 or $1 per download, we would be, I would come with my private jet probably to visit you in Singapore. But, this is, besides our work, has been very much a sort of community effort. And following the success of the handbook, in 2018, the very first edition of the Encyclopedia of Robotics was published. This is, most of the acknowledgments should go to my friend Marcello, that started this project together with Usama and myself. And the nice thing about this project is a kind of live project. It's a sort of, it's a kind of Robopedia, if you wish, or Wiki-Robo or something like that, with the difference that there is a sort of peer review mechanism in place. And so, just this is like new chapters, and as the trend, as the field evolves, just as like new areas and new chapters are added. So this is also to share that, I think we are privileged to have grown and to work in our community, because robotics community is a very live and active. And also, when I was president of IEEE Robotics Simulation Society, I wrote in one of my editorials that the spirit of camaraderie that I found in our scientific community probably has no equal in other scientific communities. And this is just the fun of robotics, and it's very kind of interdisciplinary nature. But I've been quite active, and also last year, 4 new books came out. This is a challenging project. Of course, with COVID pandemic, we learn the need of web learning education, okay? But I had recorded the contents of my textbook even before COVID, because my course, based on the old textbook, now I'm going to record, a new MOOC course. MOOC stands for Massive Online Open Course. So there are courses offered by platforms. Our Federica.eu platform is one of the most active platforms in Italy. It's the top one in Italy, and it's among the top 10 in Europe. But our courses are also available on kind of world platforms like edX and Coursera. So after the handbook, after the encyclopedia, I felt the need of offering robotics also in terms of a MOOC format. And I came up with this editorial project that I coordinated between 2018 and 2024 after the handbook, and this is the Robotics Goes MOOC project. And the illustrations on all the covers of my book are artistic work by a former student of mine. He is the CTO of Hitachi in Perth, not far from here in Western Australia, but he's also a painter and a sculptor. So he has he's designed all the images for the books that I've published. So, and the nice thing about this project is a sort of new vision of robotics that came out during a successful workshop with some people from Springer and also from Macmillan, from Springer Nature, and also from Nature, from the journal, because now Springer is Springer Nature, so with Macmillan, so it's as like Nature in the portfolio. And there were a number of scientists invited, and this is the outcome of that project that I coordinated this meeting in Heidelberg in 2017, it was 2019, I think. And this was a new vision of robotics, and which is built around 4 pillars. What are the 4 pillars? Knowledge, design, interaction, and impact. Now, when I say knowledge, as I say, I'm a control professor, so I believe in model-based control. But knowledge is not only models, it's also data. So that's why the vision is not only, it's the old paradigm is like as control people, as it just, okay, we develop a control system, we divide a mathematical model of a physical system, but it's knowledge, because behaviors and language models also, dealing with data are knowledge. And design, and I was pleased to see here that you have design and engineering, because design is not only the classical design, the architecture design, because if you go to Stanford, to the D school, design school, it's not only the old mechanical engineering concept, because design is also including issues like symmetry, like beauty. And also, if we want to make intelligent machines to become acceptable, we have to make this, just accepted by humans. If we want this technology becomes a sort of pervasive, ubiquitous. So the design aspects are very important into the development of intelligent robotic systems. Then interaction. And then I made this kind of criticism to the humanoids because it's like the challenge is manipulation is the interaction, is a human-robot interaction. That's why together with a friend and colleague, Antonio Bicchi, a well-known scientist from University of Pisa, we published a comment in Nature in 2021 in which we talk about the transition from information and communication technology to the interaction technology. And the acronym was intentionally made of 3 letters, IAT, not only to disambiguate from information technology, because information interaction would have the same initials, but also to stress the importance of the physical action that is distinguished robotics from AI. And then impact. And when I say impact, it's not only the applications, the use cases, but also all the aspects concerned with ethical, legal, sociological, and economic issues of developing this technology. And November 1st, 2024, I was at Stanford for the grand opening of the Stanford Robotics Center, and I was flattered to see that my brother, my scientific brother, Usama Khatib, just conceived the concept of the center around the 4 paradigms of modern robotics. So it was a sort of, as I mentioned, I was never a faculty at Stanford, but my relationship, my legacy with Stanford has been tighter and tighter throughout the years. And this is one other example in which the mission of a center is built around the 4 paradigms of modern robotics. Okay, this was, since I wanted to give this intro just as like, you knew some of this stuff, but I think it's nice to share with the new youngsters and the new researchers in the field. I've organized my presentation. I will devote 10 minutes to each area. It's like dynamic manipulation, aerial manipulation, autonomous manipulation, and then haptic shear control. Let's start with dynamic manipulation. And this is, again, a story because we were just visiting labs. And one night, I was in the lab with my student working on a proposal for an advanced grant on dynamic manipulation. What is meant by dynamic manipulation? Manipulation of objects in a non-prehensile way without grasping, and likewise, falling under dynamic manipulation is manipulation of the form of objects undergoing elastic, plastic, or eventually elastoplastic deformation. And this was a proposal for blue sky research with the ERC. So typically, it's very methodological. Nevertheless, being a proposal in robotics, I say we have to think about some kind of demonstrator, some kind of benchmark. And we ordered a pizza to the lab because it was late. We didn't have time to walk to the pizzeria. So the pizza arrived, and Napoli inspired me. I had a sort of illumination, a sort of idea. Let's choose the pizza as a benchmark to show the complexity of dynamic manipulation. Why? This video had, I think, several million views on Mashable platforms, was realized because when you just have the dough of the pizza, you stretch it, so it's undergoing deformation. And so, is a robot capable of doing this? I don't know. And also, seasoning is the easy part. Tossing, it's very difficult. And we didn't succeed with the electric motors because you cannot succeed with electric motor to do this kind of tossing. Baking is a control challenge because this is a pizzaiolo chef that we involved. He's been the first pizzaiolo chef in the Michelin guidebook. It's one of the best pizzerias in Naples and probably in the world. Okay, and we were acquiring his motion from an Xsense suite, and through the Jacobians, we were transforming to the kinematics of the humanoid robot that we developed, and also we developed a software with the avatar, with this biomechanical data, and so cooking the pizza is a control challenge, and I will explain this in a minute. almost lunchtime. So when I proposed this idea to my students, I said, Professor, you're crazy. We cannot ask 2.5 million to the ERC for a pizza-making robot. I said, look, the challenge is not to replace the pizzaiola. It's just to show the complexity of the benchmark. And it was also a great media expedient to attract the attention of popular media to research in robotics carried out in Naples. We were featured by BBC, by CNN, by Sky, by Scientific American. We were on page 3 on the Times newspaper of London, because the idea. And during the life of the project, from 2013 to 2019, pizza became UNESCO heritage. So you can imagine that everybody was contacting us. So this was a sort of smart dissemination idea. But let's look at the challenge. Why non-prehensile manipulation? What do you gain with the non-prehensile manipulation? Actually, we do a number of tasks in which, of course, we want to use the hands, but the power of manipulation. Remember the old concept developed by Ken Salisbury at MIT, WAM. WAM stood for whole arm manipulation. We can do manipulation also with our body, with our arms. So it's the same concept of the soft robotics, of the tentacle of the octopus. So we have to just break the paradigm that, of course, a child in the first months of their life, infants, what they do, just they grasp all the object, okay? But also we learn how to manipulate with our body, okay? And the difficulty is that the modeling and the dynamic issues of non-prehensile manipulation are very, very challenging. And it's impossible to develop a sort of general theory. So it was a sort of groundbreaking challenge that we were tackling during that project. So the best we could do is to develop some sort of manipulation primitives and to solve with some kind of model-based control techniques challenge by challenge. So we analyze rolling, throwing, sliding, friction-induced, dynamic grasping, batting, catching, pushing, dribbling are all examples of dynamic manipulation. Let me show you some results. So at first, like balancing a sphere on a plate, okay? And so this is, as you see, that's the camera, that's a visual surveying. So basically, we want to stabilize the position of the sphere on the table. This is a sort of holonomic constraints, because basically, just as the motion of the plate is 2 degrees of freedom, and that's doable. But you also see that white spot, okay? Now, we want to change, we want to control 3 degrees of freedom. So we want to control not only the position of the sphere, but also the orientation, that is that kind of white spot. And here you see the exploitation of redundant degrees of freedom in such a way as to reconfigure the humanoid hyper-redundant system in such a way to perform the task successfully. And then you can also do like, you can do sort of movement along a path with a suitable trajectory. And it's likewise, you can just do this in sort of a stable way. Then we extended this work, and now the ball is a kind of tire. And the ball can fall not only on the two sides, but can also fall just on the other side. And as you see, with visual surveying, it's capable of stabilizing the ball without falling from both sides. So it's like, so this is just to show that, and this would be a task that for a human would be very, very difficult, because it's kind of a critically stable system, as you see. Then some other example of object transportation. This was a recent paper was published in Transactions of Robotics, in which we were testing different kind of algorithms. But the novelty of this study is that we involved human subjects with a haptic guiding interface. So basically, it's like a waiter, like a robot waiter. You have to carry on a tray an object. And typically, when you do this, if you want to do this kind of task autonomously, You can, of course, exploit the constraint friction. I don't want to go into technical details. I try to give a sort of overview. So these are different kind of dexterity measures that we are using, with different conditions. And in most cases, what happens is that typically the object, just falls apart, just because of the dynamics of the task. And instead, with our kind of new scheme that we developed, in which we use, the shear control. So this is a human in the loop. So that's why this is interaction. This is a physical interaction. So you see the haptic interface, it's capable of moving the object around without falling. Okay, and this is something that I haven't seen yet in humanoids. So can you imagine a humanoid to do this? Personally, I doubt that you can do this kind of task. Just as like commanded by a human. So the second part is devoted to autonomous manipulation. And this was mentioned by Marcello when he introduced me to his students. We've been working consistently on force and impedance control. This was a study done in one of the European projects. It's the concept of variable impedance control. So basically, this is a cobot, because it's a KUKA lightweight robot, so it's compliant, but the user might be different. And this is adapting naturally to the inertial characteristics of the user to guide the user just to draw, with a pen on a sort of flat surface. And here we are testing different manipulability indexes. And the nice thing of this study, that you can adapt the parameters of the impedance in such a way to naturally adapt to the inertial characteristics of the human, just to offer the smoothest possible guiding of the pen of the robot by the human. You saw like 6 different people doing this kind of task, and this worked quite effectively. I've been teaching robotics now for 35 years. And when I go to class, one of the first concepts that I fly into the audience is that robotics is not much more than Jacobians. Jacobian, in my opinion, is the most important mathematical tool for Jacobian. And this is one example. Now we go back to prehensile manipulation, like with the hand, okay? And the problem of mechanical hands, of robotic hands, is the mechanical complexity. Because a hand has 20 more degrees of freedom, and it's impossible to conceive a hand with 20 motors. This would be very, very, very primitive. So one trend in designing anthropomorphic multi-finger hands was the concept of minimalism, the concept of reducing the number of motors and use cables and tendons to achieve the actuation with a reduced number of motors. And actually, this is one example of cross-contamination with another field, because a colleague of ours at the University of Arizona, Marco Santello, a neuroscientist, developed a very nice taxonomy of all the possible grasps of a human hand, and he classified 36 different grasps. And the nice thing is that these grasps, actually humans do not move the individual phalanxes of the fingers. You really have to think intentionally to move a single phalanx of a finger. We move the hand and the fingers in a sort of synergetic way, even the infants when they grasp the object. So his studies show that the concept of the concept of postural synergies. What is this concept of postural synergies? It's very simple. Basically, the motion is not of the individual finger, but you move the fingers all at the same time. And this is one example where the mathematics is beautiful, because this is nothing else than the principal component analysis of the grasp matrix, singular value decomposition. So you compute the main eigenvectors of the singular value decomposition, and the nice thing is that with the first 3 eigenvectors, these are the so-called postural synergies, you can describe more than 80% of the taxonomy of the grasps by the neuroscientists. So this is amazing. So in a way, it's why should we dare to control 20 plus degrees of freedom? So this can be used in terms of the suitable Jacobian, the suitable mapping from the motor subspace, from the motor synergy subspace to the Cartesian space. And it's all a game of Jacobian to describe. But we could use this into a sort of constructive fashion to rethink the design of hands in such a way to have a sort of hand with one motor, with two motors, and with a system of cable and tendons to achieve the different degrees of freedom. So this is the concept of mechanical synergies. And we apply this kind of framework within, you might, I mean, if any of you has studied on any of the textbook, you know the famous click concept. The click concept is the closed-loop inverse kinematic concept using the Jacobian inverse or pseudo-inverse or the Jacobian transpose. And this is one application. I made one mistake when I wrote the first paper in transactional systems and cybernetics in 1986, because before submitting the paper, I should have patented this, because this has been, but at that time, you know, I was a young PhD student, a young PhD graduate, so I was only daring for the glory. I didn't think about, you know, just making profit about this. But the click, you know, this concept has been used in all commercial systems. And we extended in this study, this is the Schunk 5-finger hand, in which we use the concept of the Jacobian transpose. The novelty here is that we provide the reference motion according to a synergy-based framework in which we also exploit feedback from the encoders and also from a force sensor. We use like a force torque sensor. I think this was a JR3 sensor, if I remember well. So we can generate the design motion also with a sort of grasp optimization technique in which we optimize a synergy-based quality index, because we have to ensure that the grasp satisfies the so-called force closure property. This new stuff is in the new textbook, because we included cooperative manipulation and grasping, which was missing in the old textbook. So this works quite effectively for different kind of grasps. Also, I mean, I decided to just show some sort like 4 or 5 slides for each research area. We applied this concept with a synergy-based method to train the neural network for some reinforcement learning technique. This is the classical PI2 learning process in which we have, you know, like the agent is the robot, the environment is this kind of unknown object, and through a sequence of repetitive trials, you know, the system adapts and learns how to grasp an object of different shape and size. And also, there is a sort of reward function that is driving the neural network, in which we achieve a sort of trade-off between the exploration by the hand of the environment and then recognizing the object, and the exploitation of the characteristics of the grasp, you know, just to recognize how to properly grasp the object. And this worked quite nicely. As I mentioned, aerial manipulation became a main topic into the research team. And again, there is an anecdote, a story behind this. I remember this was 2009. I got a phone call from a colleague and a friend at University of Bologna, Lorenzo Marconi. He's a control guy. He had started working on aerial robotics because he always was using drones also for photography and things like this. And so he called me, say that I'm proposing this new project, European project on aerial manipulation. So I told to my guy, Vincenzo Lipiello, who had finished his PhD on visual servo, I say, look, you know, that's very nice consortium, strong partners, you know, with Aníbal Ollero from University of Sevilla, big name in aerial robotics. There was, I think it was DLR, which is also involved, the Center for Robotic Mechatronics in Wesseling, near Munich, in Germany. And then I told to Vincenzo, I said, let's take part into this project. They say, no, but we don't have any background on aeronautical. We don't know, yeah, but we know, we can derive the dynamic model, and we know what kind of sensing, what kind of sensory feedback control technique we can develop. Believe it or not, after the iRobots project, we got another 7 projects funded at the European level. So in 11 years, we got 8 projects in aerial robotics funded. And we have become one of the top teams in Europe in terms of funding on aerial robotics. And Vincenzo himself made the spin-off in 2018, which is now the startup company of Neobotics. So, you know, it's just like, I understood that the challenge of having a flying hand besides a flying eye was very much pertaining to robotics. So I'm going to show you some of the work. This is This is not the iRobots project. It's a following project. It's the ARCAS project that we did with DLR and Sevilla and other partners, in which we were using the KUKA lightweight arm as a payload for a huge octocopter. So this drone has 8 powerful motors. Of course, autonomy is always a challenge, but we have some experiments of crawler deployment and retrieval. So you can control all the degrees of freedom of the system to do some sort of tasks autonomously using the well-known KUKA lightweight robot. And so with the very high payload capacity. Another example of manipulation with the sort of bimanual system. So this is the ARCAS project. ARCAS stands for Area Robotics Cooperative Assembly Systems, in which this is all autonomous. So we have an X8 drone base with a 6-degree freedom active robot arm, like each drone, and then 1 degree of freedom gripper. And this is a typical industrial environment, clutter environment. So the system is avoiding all the obstacles. And so you carry this. This is typical mounting of a sort of truss structure in which we do cooperative transportation and deployment. Then I have another application for power grids. This is a task that is both expensive and also sort of dangerous to do some sort of inspection and maintenance and repair of the power grids. And here we brilliantly solve the issue of autonomy of the drones by installing some autonomous recharging station on the line to exploit the magnetic field and to have the drone not to fly back but to recharge while on the line. And the issue here is the installation, removal, or repair of all kinds of devices. So the system can be teleoperated, if you wish, by a train operator. But then, it flies on the line. Just then, it just lands, and then it has some kind of rolling wheels to go along the line. And this is, for instance, the installation of a bird diverter, because when the bird migrates, they tend to just sit on the line and they overload the line, and the line can be even broken because of the weight of many birds, or maybe they get kind of dirty. So they use this kind of bird diverter. And the nice thing of this project is that recharging the system using the power line energy. So basically, you can exploit the fact that you're repairing a power line, electric power line. So why not, not use the energy? For some of these tasks, like the operators are flown by helicopters with some kind of ropes. So it's a task which is very expensive and also a sort of dangerous for the operator. Another application of aerial robotics technology is in non-destructive testing. Think about the tragedy of Morandi Bridge that fell down in Genova in 2018, 8 years ago. And 43 innocent people were killed because the bridge collapsed and the people just driving with their vehicles on the bridge, just they fell down and 43 people were killed. This was also because of lack of systematic inspection and maintenance of civil infrastructure. So this is another application that we developed in which we implemented our techniques for force motion control, developed originally for ground-based manipulation, to the concept of aerial manipulation. So this is active interaction force control with, in which we have a 5-degree freedom lightweight robot arm with this X8 drone base, and And we are just testing the walls to see if there is any crack, if the wall is integer, to check the integrity of the wall. And also it's nice because we develop hybrid force motion control in which we apply 3 Newton to the wall to check the kind of structural resistance and integrity of the surface. And also the tool that we've developed is a multi-sensor tool for non-destructive testing that includes UT, EMAT and eddy current sensor. Another example of interaction technology, I would say. And I'm kind of skeptical about generative physical AI to do this kind of task, honestly. So another application is, this is a 26 degree of freedom drone that we developed, we designed in the house. And this is, again, aerial non-destructive testing on pipes. Think about oil duct or a gas duct. And we want to check the thickness of the pipes to see if there is a potential crack. Because if there is a leak of gas, of oil, is also a cost involved into that. So the system flies, lands on the pipe, then have some rolling omnidirectional wheels, and then just goes with this tool, this is a thickness tool, and checks systematically, the thickness of the pipe. And there is another version that I cannot show because, it's part of the startup work in which we just improved this concept with a sort of koala robot. So basically, the drone flies this koala robot on the pipe and then flies away. And with very little energy, this kind of koala robot just checks all the pipe and also can just revolve and check the thickness of the pipe. I also have another application, but in interest, we also developed some hybrid drone, amphibious drone. This is very much, I like it, the bio-inspired nature of this kind of technology. The thing is to develop a sort of metamorphic robotic system in which we can use the rotors of the drone also to provide some sort, once it lands on the water, some sort of propulsion, to avoid just flying out and land on another place, but also, just to be able to kind of navigate and to do some sort of probe testing, for just checking maybe some sort of pollution in the water or any kind of test. But I didn't include any slide. The final part is about haptic shear control. What is haptic shear control? It's like, you have the two extreme, teleoperation or autonomous. If you have the human in the loop through some sort of haptic interface, you have to trade off the control authority between the human and the machine. This is what is meant by haptic shear control. So those are systems in which a human operator trades the control of the remote robot with an autonomous control for achieving a common goal. And the task of the autonomous control is to reduce the operator's physical and mental workload. So in some portion of the task, the operator can be naturally guided by the robotic system as assisting, just in a way that, and you can also satisfy any kind of constraints. So this is, for instance, one application with the bimanual manipulator. So we have a dual-arm semi-autonomous system. We use vision-based control and collision avoidance. And through the haptic guidance, you're naturally led to avoid any kind of joint limits, mechanical joint limits, singularities, and also collision with potential object into the field. And also in this study, this was a work that we did with a group in Rennes, is the group of Paolo Robuffo Giordano. He's a CNRS research director and is working at INRIA in Rennes. And Mario Selvaggio is one of my research associates, tenure track assistant professor, did this work. I think we published, I can't remember whether, I think it's Transactions on Robotics or maybe Robotic Mission Letters, one of the two journals, in which we have, because with conventional teleoperation, there is no haptic feedback, there's no kinesthetic feedback. So you gain this if you have a device that allows you to really to trade, what is your human workload. And also, we apply this concept for medical robotics, in particular for the context of robotic surgery. When the surgeon operates, even with the Da Vinci system, one of the time-consuming and stressful phase of a surgical operation is the suturing. And typically, and you cannot make mistakes in suturing. Actually, if you have removed maybe a cancer mass or like an organ, you have to reconstruct the anatomy of the tissues. This is what is called in technical field as anastomosis. And you have to, and the manuality and the dexterity that is required is very accurate. So the concept here is to use the variable impedance concept that I showed in my previous slide through an haptic interface to provide a sort of guidance for the surgeon to suture the tissues in the most optimal way. And this is the concept of virtual fixtures. So remember, from the ontological viewpoint, the responsibility of any surgical operation always stays with the surgeon. And it must be that way, of course. But in a way, the system can guide the surgeon to suggest what are the best paths to do the sort of suturing. So this is the concept of the virtual fixture. And as a final slide, I have an application of my current grant, the Synergy grant. This is a very important social challenge because the overarching goal is to fight colorectal cancer. Colorectal cancer is the third worst cancer killer for humans. And the data in Europe say that the mortality rate is 50%. Why is so high? Because the level itself of mortality of cancer, if diagnosed in time, is not as bad as other cancers, like, for instance, pancreatic cancer, which is fatal. It has a level of mortality, if diagnosed in time, comparable to breast cancer, to prostate cancer. But why in Europe in 2020 there were 600,000 of cases diagnosed and 300,000 people died? So this is unacceptable. Why is that? Because people do not undergo systematic screening. Of course, at my age, I did 2 colonoscopy already and 1 gastroscopy. And next year, I'm scheduled for the next colonoscopy and gastroscopy. That's the best that we can do to diagnose in time. And also, the problem of this is that typically, how is this performed? Through a colonoscopy. That's the most reliable exam. But the manipulation ability of a colonoscopy is very reduced. Only the skilled endoscopist can smear the polyp. Polyp is a sort of suspect cancer mass, but the excision of the polyp does not guarantee that you have safe oncological margins in such a way that the cells are not spread to the near organs, and this might cause a metastasis. So it's a procedure that is carried out in 2 stages. First, you do the diagnosis, then you analyze the tissue, analyze the cell, and then you go back with the surgery. Either with the colonoscopy, with the skilled endoscopist, or in laparoscopy or in open surgery, depending on the stage of the polyp. The stage is the level of cancer mortality, okay? The problem is that when this kind of cancer is diagnosed, it's typically stage 3, stage 4, and it might be too late, okay? So together with the 3 colleagues and friends, we're working on this idea of developing a sort of revolutionary technique of theranostic type. What is theranostics? It's the possibility of doing the therapy during the diagnosis. And this is very much in line with the trend in medical and surgical robotics that goes under the name of nodes. Nodes exploiting the natural orifice transendoscopic surgeon to exploit the orifices of the human body. Okay? So our goal is to develop a robotic system that can diagnose and operate and do the therapy in one shot during a single colonoscopy. And so we came together with different expertise. Alberto Arezzo is a surgeon at the University of Torino, is the current president-elect of the European Association of Endoscopic Surgeons. is like one of the top European surgeons for colorectal cancer. And Kaspar Althofer is director of the Advanced Robotics Lab at Queen Mary University. He was the general chair of ICRA 2023 in London. He's an expert of soft and inflatable robotics. And then Sébastien Ursulin. He comes from the French School of Computer Vision. He was a PhD student of Nicolas Ayache. Nicolas Ayache was a pupil of Olivier Faugerat. Olivier Faugerat is considered to be the father of computer vision from INRIA. And Sébastien, he leads a big group at the London Institute of Health Engineering at King's College in London. It's funny, none of them is British, because one is German, one is French, but they are in UK. And thanks God, despite Brexit, we can do European projects with them. Now they're changing. They want to go back to the funding system, because it's like, and he's a big expert in AI and medical imaging. I think his H index like 150 to 200 is like one of the big names. And then my team on control and manipulation. So I have, and we submitted. There was several submissions, and finally we got funded. Ho finito, questa è la mia ultima slide. And finally, we got this project funding. And I have a 2-minute video that illustrates the concept, and then I'm done. So this is our patient on the table, ready for a colonoscopy for inspection. And the novelty is to use a sort of tip-growing mechanism, it's pneumatically actuated. This is the concept of a version robot. So this adheres to the walls of the colon, and can also do some sort of rinsing of the residual phases after the purge, the preparation that you have done in the previous day. So this creates a sort of shuttle for a robotic capsule to be inserted, to be manually tethered, and inserted this 12-millimeter robotic capsule. And the capsule is sensorized in such ways to detect the suspect polyps. I have a close-up view of the capsule in a few minutes, and then goes to the bottom of the column, and then how to operate. And our idea was to use the negative gradient of pressure in such a way as to suck the polyp into the operating theater, okay? Because you need a sort of clean environment to operate. So this is our capsule. That's the rinsing channel there. And it's like stereoscopic vision, white light illumination. And this is a multi-sensor probe, which is exploiting all optical ultrasound together with a technique which is photoacoustic endomicroscopy, because some of the adenoma are flat, and it's very difficult to understand how to excise and how deep you have to excise. So that's why you need the diagnosis. And then this is a bimanual micro-manipulator, one with one arm with a cutter, another one with a fenestrated grasper. And the technology we are using to develop this kind of system is that I was discussing with Cecilia during the visit is the concept of concentric tube robots. This is the technology that we are using. So that's the concept. And then you can aspire, and then you can drive back, and then just remove. So the idea is to do this kind of colonoscopy with diagnosis and surgery in one stop. That's all I have. I cannot avoid concluding this with my inspirational motto. We in 2002 in Sant'Angelo in Ischia at ISER, that we organized ISER, International Experimental Robotics, and Roland Sigvart, our friend from ETH in Zurich, was committed to organize the next edition of ISER. And thanks to a very good bottle of wine after dinner we were enjoying, I came up with this, Roland, you have to keep the gradient. And then this has become a sort of inspirational motto. Of course, you are all in mathematics, you know what is a gradient, but gradient is a derivative of a function of multiple variables. And the multiple variables are the variables of life. So keep the gradient is a sort of motto that you have really to really consider all the variables in your life, and possibly to just move and go ahead along the positive direction of the gradient. Thank you very much indeed.
Thanks a lot. Thanks, Bruno, very much. I'm sure there are some questions from the audience. I hope the students have been inspired by your talk. Don't be shy. If any of you has any question or comment, yes, please.
Yes, please.
About manipulation, about the manipulation and the areas you showed just now, how do you foresee like the industrial growth in robotics? How is it applied to the industry?
I didn't get your question.
Okay, so in the next decade or so, how do you foresee like how will robotics spread to like the industries in the next decade or so?
Manipulation tasks?
Well, as I say, like I think the advancement on locomotion and also the technology of the arm is really well progressed. I think just as like manipulation is not as established. If I made the example of dynamic manipulation, but also you can think about sort of prehensile manipulation. The thing is that just it's a sort of I think that it's not only the you can develop the most performing control technique, but in my view, you have really to rethink the design of the effectors to do the manipulation, and it's not by chance that just looking at the nature, we see some kind of natural way of doing manipulation, which is not the way a mechanical engineer would typically design. And also, I think that while you can say that for the locomotion and for the sort of mechanical arms, you can have some kind of general purpose systems, if you want to develop this concept at the level of manipulation, then you have to really look at some device, some kind of tool that can be as simple as effective for the specific application. And I think this is something that in our field is one of the big challenges. I also suggest you to, there's a very nice blog that I'm following. It's a blog by one of our colleagues, is a professor emeritus at Carnegie Mellon University, Matt Mason. Matt Mason can be considered one of the fathers of manipulation. And if you Google Matt Mason robotics blog, there is one of his blog is devoted exactly to the challenges of manipulation. And he really criticizes the fact of why should we develop, for instance, like humanoid or caninoid or any kind of system. Just as like it's not only the fact that they replicate, just the biped or the quadruped. It's just the kind of it's the manipulation application that distinguishes and also gives a specific character to the robotic system that you want to develop. And there are many examples in nature like this, like fish, like just different kinds of animals. And you have to look at this, and it's something that is not be fully exploited yet in robotics. And I think this is one of the new challenges. And the whole area of soft robotics, and also the example of inflatable robotics is going along that direction. So I really advise you to check. There is one blog of Matt Mason devoted to manipulation that is very, very inspiring, in my opinion.
Thanks a lot. I know the blog is...
it's nice.
Yeah, it is. I saw, a hand on this side.
Thanks for the talk and thanks for the handbook of robotics. So my question is on the autonomy. Let's say with the advancements in AI and the way the control and manipulators of advancing, do you foresee any autonomy that's going to be completely humanless?
Yeah, I mean, just as like humanless. Depending on the task, just as like some tasks, it makes sense to be completely autonomous. I'm not against, just as like, especially because I mean it's like the social cost of labor, and I know that as we were discussing in this country, in Singapore, this is one issue. with all the immigration and so I think personally I think some tasks if the task is repeatable and can be automatized, can be made autonomous, that should be the case. And in fact, I didn't present this, but I am for a sort of humanism vision of technology, a sort of technology humanism. So in the same way as we take advantage of our navigator, our translator, just like, if we use like Claude or ChatGPT, I think it's fine. Because, what technology does is like increases the average level. But then it's the ability of the single human that distinguishes, one application from another. So, I'm not again, personally, I believe into the value of developing sort of hybrid control strategies in which you try to merge the model base, because for deambulation, for locomotion, for gait, you need the models, okay? And then you can take advantage of the data, just to merge some sort of data-driven technique, using, for instance, in the theranostics, just the diagnosis of the polyp is done with some AI technique. We use the concept of AI guardian, in which we take advantage of data sets of that kind of pathology of cancer. And also, you can exploit the data set not only of the environment, but also of the surgeon, because you can improve your skills through the data set of previous operation. So that's the way, in my opinion, to go for developing advanced intelligent control systems.
Another question here,
yes.
Maybe last one, because...
amazing talk. So I work in haptic information back.
Yes.
And it's kind of a related question to the last one, is that if you have a completely intelligent autonomous robot system, then you no longer require haptic feedback to humans to provide more information. So how do you see the haptic feedback information work in the future of robotics?
My answer, I give you a sort of indirect answer. I presented some stuff on surgical robotics, okay? And your question is very relevant. Why? Because in the training center in the polyclinic, we do the training of the surgeon trainees to the Da Vinci system. Okay. Now, if you take a 40-year-old, don't think about a boomer like myself. If you take a 40-year-old or 50-year-old surgeon, okay, and using some sort of MR images, magnetic resonance images, she brings the expertise of that image concerned with a sort of tactile perception. Because in open surgery and in laparoscopy, with the laparoscopy, how is laparoscopy different from robotic surgery? Because with the laparoscopy, you touch, and through the trocar, you have the tactile perception of touching. The problem with the digital generation is that they were born in digital age, and they don't have, for them, the images is just image, it's just the data. It doesn't necessarily relate to the tactile experience. So that's why I think it's the crucial challenge of developing, it's like the concept of developing a sort of tactile internet. So during the pandemic, we did the smart working, but we didn't do the physical smart working because all the manual, all the physical actions, they were shut down because we were still unable to control a machine with the sort of human in the loop. So that's the challenge that we have to develop. So I gave a sort of indirect answer just to show, what in my opinion is a kind of complexity. So we must, just haptic devices are great devices, but the status quo technology, Da Vinci system, is only a filtering of the tremor, has no feedback, it's not kinesthetic feedback, it's not tactile perception. Whereas in laparoscopy and open surgery, the surgeon has also brings a sort of burden of expertise of relating the images to the sort of tactile perception that the new trainees in surgical robotics don't have. So we are mandated to develop this kind of technology.
Okay, thanks a lot. So we thank Bruno again for the great talk, very inspirational. Thanks a lot for coming. As you know, thanks you all for attending. As you know, this is part of the NUS Robotics Seminar Series, so it's recorded and will be in the repository. This is supported by the Advanced Robotics Center. Stay tuned for the next seminars.
And I can
Thank
also
you.
share the slides if you want.
Wait, when you start recording again?
In the Advanced Robotics Center website, ARC website. Okay, thanks again.
Thank you again.